Hello, everyone. So this is the last activity of Machine Learning Summer School 2021. So it is very nice that you are still here. And this session is the panel of self-supervised learning and universal modeling for speech and audio processing, benchmarking, and open source toolkit. Before we start this panel, let me introduce our panelists. We have Professor Shinji Watanabe from CNU, Dr. Shang-Wen Li, we call him Daniel. He's engineering and science manager from Facebook AI. Professor Titouan Parcollet from Avignon University, and Dr. Mirco Ravanelli from Milan. So this is our panelists. And we already talked about something related to speech in this machine learning summer school. So we have talked about deep learning for speech processing. And what we have learned in the previous lecture is speech processing is not as difficult as you imagine. If you are familiar with deep learning model, you are already prepared to engage in speech technology. So you can have a sequence-to-sequence model, take speech as input and output text. So you can achieve speech recognition and speech translation. Or you can extract speaker information to do speaker identification and speaker verification. Or you can do emotion recognition to extract some processing information from speech. And you can also have a model take speech as input and speech as output. This is speaker separation and voice conversion. You can also do text to speech. You can also do TTS. So you already have the rough idea about those models. But how to implement those models? Today, you will find that it is much more easier than you expected. Besides training the model, we also have to consider data. To train a model, usually we need some peer data. To train a speech recognition model, as I have told you last week, that a commercial system usually uses more than 100,000 of hours of peer data to train a high-quality speech recognition system. However, there are lots of different tasks in all the different languages. There are more than 7,000 languages in the world, and each language has all the different tasks. It is impossible to collect sufficient peer data for all the different tasks. However, when you consider human baby, they learn their first language almost without supervision. Can AI have the same ability? This is the question we are going to ask in this panel. And probably the answer is yes. We already see some potential from the previous lecture. We have a lecture about self-supervised learning for natural language processing. So in the previous lecture, we already learned that we can collect lots of unlabeled text, and you can pre-train your model, and you can pre-train based on the unlabeled text, then you have a BERT or GPT. Then you can use those self-supervised model in the downstream test. For each downstream test, you only need very limited label data. You fine-tune your self-supervised model, then they can work well on those downstream tests. But this is for natural language processing. In the previous lectures, all the examples are about natural language processing. Can speech do the same thing? How about speech? Can we do the same thing in the speech community? So this is the outline of today's talk. So in this panel, for the part one, we will talk about some benchmarks for self-supervised learning for speech-related tasks. We will talk about Superb and La benchmark. And then we will talk about the open source toolkit for a wide variety of different speech-related tasks. So you will see SpeechBrain and ESPNet. And during the part one, please feel free to type your question in the chat room. We may not answer your question immediately, but please leave your question in the chat room. In the second part of the panel, we will discuss your question. So let me start to talk about benchmarking for self-supervised learning. And besides Superb and the benchmark, we are going to talk about that after a few minutes. There are other benchmark corpus about self-supervised learning or unsupervised learning for speech processing. So there's another corpus called Zero Speech and another corpus called Here. Actually, they are both challenges in NeurIST 2021. I put the link of these two challenges below for your reference. Let me describe the role or the difference between those benchmarks. For Superb and the benchmark, both of them use speech representation in a wide variety of downstream tests. So in the downstream test, we still have some label data. For Zero Speech, they assume that no linguistic labels are available because, as you know, some languages even do not have the writing system. So some languages do not have any linguistic label data. So how can we deal with this problem? This is the target of Zero Speech. And these three corpora are focused on speech. For Here, is focused on audio. Probably not all of you know the difference between speech and audio. Audio is something like music, some event, someone dropped something, someone closed the door, something like that. So Here is focused on audio, and those three corpora are focused on speech. So let's start from Superb. Superb is speech processing universal performance benchmark. So lots of research institutions involved in this project include National Taiwan University, CNU, NIT, Johns Hopkins, and Facebook AI. Today, due to time limitation, I can only provide a very rough idea about Superb. If you want to learn more detail about Superb, please read the paper we are going to publish at InterSpeech 2021. And you can find that this is a project involving lots of researchers, and both Shang-Wen Li and Professor Shinji Watanabe are also the member of this team. So before Superb, there are already lots of research targeted at self-supervised learning for speech. So before we have Superb, lots of research institutes have tried to use unlabeled speech to pre-train the model, then have a self-supervised model. And there are already some very well-known self-supervised models, including CBC, PES, APC, Monkey-J, Web2Vec series, and Hubert series. However, we found that those papers usually use different data sets, so we cannot compare those data sets side by side. We cannot compare those models side by side. Usually in those papers, they show that they are better than the typical acoustic feature like F-bank, but there is not too much comparison between different self-supervised features. And in most of the paper, you can find that most of the authors only apply those self-supervised models in speech recognition. So people may ask, how about other tests? At the beginning of this talk, I have mentioned that there are lots of different tests in speech processing besides speech recognition. Will supervised models work on those tests? We don't know. So we want to try more different downstream tests. So this is the basic idea of Superb. You can consider it as the decasome of self-supervised speech model. So those self-supervised speech model are the athletes. So they are going to participate in a series of speech processing tasks. So we have lots of different tasks, and we are going to use this model in all the different tasks to compare their performance in all the different tasks. And please let me briefly introduce what are the tests, what the tests we have. If you cannot really get this part, don't worry. So this is not very important. I will go through all the tests very, very quickly. So we have some tasks related to content information. So we have phoneme recognition, recognize the phonemes from speech signal. We have keyword spotting, determine an audio segment belong to which keyword. We have typical speech recognition. I do not have to describe what is speech recognition. We have query by example. You have a long spoken document and you have a spoken query. your model have to determine whether the spoken query exists in the spoken document. We have some tasks related to speaker. So we have speaker identification. You have to determine this utterance belong to which speaker ID. And you have speaker verification. Your model have to determine given two utterance whether they are from the same speaker or not. And we have speaker diarization. This is a very sophisticated task. Machine will given something like a meeting record, and you have to determine which segment of audio belong to which speaker. So this is speaker diarization. We have a set of tests related to speaker. We have some tests related to semantic. So we need a model. We will go. The model have to take an utterance as input and output the intention of the utterance. The model have to take an utterance as input and extract the value of the slots. You have to know that Taipei is the destination, or New York is the destination, and Taipei is the front location, something like that. You have to extract this kind of information. And in natural language processing, there are, of course, lots of models can do that, extract those kind of information from text. But here we have to extract those information directly from the speech signal. And we have emotion recognition. The model have to take an utterance as input and output the emotion in the utterance, output the emotion of the speaker. So we have 10 tasks in the Superb at this moment. And before we go through the results of this competition, I will going to introduce the track of in the Superb. So there are different ways to use the self-supervised model. So different way to use the self-supervised model corresponding to different track. And here, due to time limitation, I'm only going to talk about the constraint track. So in the constraint track, we use the self-supervised model in this way. The parameters of the self-supervised model is fixed. So we fix the parameter of self-supervised model. It will not going to be updated. So the self-supervised model takes speech signal as input and output a set of acoustic feature. And no matter which downstream task it is, we use the same self-supervised model. One model is used in all the different tasks. And for all the downstream model, we predefine its network architecture. So for all the different self-supervised model, they use the same network architecture in the same downstream task. And here the policy of define the downstream task network architecture is we want to keep it as simple as possible. If we can use linear model to solve a task, we use linear model. We use more sophisticated model only because linear model is impossible to solve the task. So we try to make the network architecture as simple as possible. And in the next slide, I will going to describe what does this setting mean. If a self-supervised model achieves good performance in this setting, what does it mean? So as I have mentioned, the downstream model is as simple as possible. So the downstream model only have very limited capacity. It's very weak. It is not very powerful. So it cannot do lots of different things. It is very weak. So it has to rely on your self-supervised model. However, the self-supervised model is fixed and it is shared across different tasks. So it is task independent. You have to use one model to support all the different downstream models, which are very weak. If a self-supervised model can successfully work well on all the downstream tasks, even though the downstream models are very weak, that means the self-supervised model can extract universal features. So it can extract the feature. It has general purpose knowledge for all the different speech processing tasks, probably from low-level acoustic signal to high-level semantic information. If we have this kind of universal feature, then it would be very easy to add new tasks. As I have mentioned, there are many different kinds of tasks in speech processing. So 10 tasks do not cover all of them, only cover a very small amount of tasks. So if you want to build a new application, it would be easy with this universal model because the downstream model is very small, very simple. So you only need a little bit task-specific data to train the downstream model. So it is very easy to add new tasks if we have universal feature. And if we have universal feature, you do not have to build a model for all the different tasks. You can save your storage because in your cell phone, probably it has one model for speaker recognition, one model for speech recognition. It has different models for separate tasks. But in the scenario here, we use one universal model, one self-supervised model to support all the downstream tasks. And if this can be true, then we only need one model as the backbone, which can support a wide variety of different tasks. This can save the storage. But this sounds too good to be true. Can self-supervised model really achieve that? Can self-supervised model really extract universal feature? This is the question. Before we take a look about the experimental result, let's first say how we extract the features. So this is the self-supervised model, takes speech signal as input, and each layer output occlusive feature sequence. Then we don't know which layer should we take. Which layer should we take as the input of the downstream text? So how to solve this problem? What we do here is we weighted sum the features from each layer. So for example, this embedding is X1, this is X2, and each layer has a specific weight. Then the embedding, the representation here is the weighted sum of all the different layers. And the downstream model take the weighted sum of different layers as the input. You may wonder, where is those weights come from? Those weights are jointly learned with the downstream model. You can consider those weights as the parameter to be learned, and it will be fine-tuned jointly with the downstream model. And here is some experimental result. We have a very big table here. I'm only going to summarize the result. So these are different tasks, and we use open data for all the different tasks. So it's very easy to reproduce the results here. And the baseline is FBank. We already mentioned FBank in our previous lecture. As I have mentioned, FBank is probably the most popular feature for speech recognition. And we have all the different self-supervised speech model. And we found that, first of all, if we compare the result of self-supervised model and the FBank, in general, in most of the cases, self-supervised learning outperform the baseline. So it shows that self-supervised learning is truly helpful. And not only in speech recognition, as previous work shows, it is in general helpful in lots of different tasks. And there are several models which are general. I mean, there are several models which can outperform FBank on all the 10 tasks in Superb. Okay, and if we compare the performance of different models, we can find that Huber and Web2Vec 2.0 outperform other models. And now we have a leaderboard for Superb, and you can submit your result to the leaderboard. So if you have any good idea, if you think you can train a model better than Huber, and you are welcome to submit your result to the leaderboard. Tell the whole world that you get a better self-supervised model than the state-of-the-art self-supervised model. And probably you will think that training self-supervised model can be difficult, and there are lots of different downstream tests in Superb, and probably it will be very tricky to submit a result. But actually, it is not. The Superb team also built a toolkit called S3PL, and I also put the link of S3PL here. And S3PL support retraining, and you can access other self-supervised model through this toolkit, and it can help you to, you can use this toolkit in downstream fine-tuning, and it is also helpful. You can use this toolkit to support you in Superb challenge. And here, I would also like to mention that this toolkit is helpful, is used in SpeechBrain and ESPNet. You will see more results in the following talk. And here, I will let the two main contributor of S3PL to talk about this toolkit. So Su-Wen, Leo Yang, and Andy, they will talk about this toolkit. They already have their recording here.
Hi, my name is Andy. Today, Shu-Wen and we are going to introduce the S3PL Speech Toolkit. S3PL stands for Self-supervised Speech Pre-training and Representation Learning. Here, we will start by giving an overview of the whole process. First, if we have some unlabeled speech data, we can do some self-supervised learning. In self-supervised learning, what we are basically doing is pre-training some neural networks. Once pre-trained, these neural networks then can generate some meaningful representations. And finally, the pre-trained neural network and representations can be used on several different downstream tasks. Here we only list a few of them. In this talk, we'll refer to the neural network as upstream and these tasks as downstream. Our toolkit mainly provides 4 main features. First, the upstream pre-training. Second, the upstream hub. Third, the downstream fine-tuning. And last but not least, we support the superb challenge. We will go through each feature one by one. First, we will talk about the upstream pre-training part. Currently, we support the pre-training of 3 different methods. First, we have the Mockingjay, which is basically the speech version of BERT. Next, we have Audio Albert, which is basically the speech version of Albert. And third, we have Terra, which is an improved version of Mockingjay. These methods are fairly similar. First, waveform is converted into spectrograms. Then, after some downsampling, the spectrograms are randomly masked. After passing through some transformer blocks, we will generate some representations. And after a linear transform, we will try to predict the mask spectrogram, and the model are learned with L1 loss. Now we are going to talk about feature 2, the upstream hub. Here we list some popular models that we currently support. In our upstream hub, we provide an all-in-one unified interface. All these methods may come from different implementations. However, with our toolkit, you can access them easily and switch between different models, or jointly use more than one at the same time. Initializing your model is as simple as the following. You basically only need 3 lines of code, and you can build a CPC model. Here we show the first method that you can use to initialize your model. We provide an alternative method too to initialize your models. Here, you can change the string to switch between different models. Plus, we provide automatic preprocessing. All the upstream models take raw waveform as input, and our toolkit will automatically apply the corresponding preprocessing on the fly during model forward. Next, I will talk about the input and output format that our upstream models adopt. The input is a list of unpadded waveforms. The list symbolizes a batch, and each waveform should be a torch float tensor. The output is a dictionary with at least 2 keys, hidden states and last hidden states. Last hidden state is a tensor in the shape of batch size, extracted sequence length, and feature dimension. And hidden states is a list of tensors all in the same shape, same as last hidden state. However, the hidden states contains the hidden states from all the hidden layers of the model. This covers our upstream hub. Now I would like to invite my colleague Su-Wen to introduce the remaining 2 features, downstream fine-tuning and the superb challenge.
Thanks, Andy. Hi everyone, I'm Su-Wen Yang. Downstream task evaluation are essentially important for self-supervised learning, since we basically know nothing by looking at the pre-training loads. If the pre-training learning scheme is too simple, you can end up very small loads but learn nothing. So we should always evaluate representations on downstream tasks to see whether the new ideas work. Hence, we provide a wide range of downstream tasks to ease this implementation burden, let you focus on new ideas of upstream pre-training and easily evaluate with our downstream modules. Instead of providing many generic speech modules and models as already done fantastically by ESP.NET and SpeechBrain, we opt to provide the module for a task called Downstream Expert, which you can just plug and play to evaluate your upstream model as soon as possible. After downloading dataset like LibreSpeech, you can change the dataset path in the YAML file, which configures the Downstream Expert. Then, the expert will initialize the dataset and provide the suitable downstream model accordingly. After initialization, you can get the data loader from the Downstream Expert, which you iterate for new batches. By feeding new batches into the forward function, you get the loads and train the expert. Finally, the expert also defines how to calculate task-specific metrics and logging. Here is a very simple conceptual pseudocode on how things work. First, you import an ASR module from S3PL downstream. Then, initialize it with the YAML config containing your LibreSpeech path and get an expert. Iterate over the data loader given by the expert and forward the batches into the expert. Finally, log the results during the model forward also by the expert. You can either use the Downstream Expert with your own training evaluation loop and optimizers, or you can also drive the Downstream Expert with well-written trainer classes provided in other toolkits like PyTorch Lightning, Hugging Face, ESPNet, and SpeechBrain. We also provide a simple fine-tuning script to serve this purpose, where you specify on the command line about which upstream model you want to evaluate and which downstream task you are interested, and then the script will do the fine-tuning. You can also specify many training hypers through command line, like learning rate optimizers or the training steps. The final feature is that we include all the tasks defined in Superb benchmark in S3PL. So by the fine-tuning script I just mentioned, you can conduct experiments for all pairs of upstream and downstream. To benchmark new upstream model, you can upload your model definition along with pre-trained weights to either Torch Hub or Hugging Face Hub. The fine-tuning script will then download the upstream from the internet and do the fine-tuning as before. And after the fine-tuning, the script will also generate the prediction files for each task for you to submit to our online leaderboard. Here is a brief navigation through our leaderboard website, the landing page, and some useful links, the task definition, and the rules for the submissions. And here is the leaderboard containing all the results, and you can toggle a task to choose which task you want to show on the leaderboard, or you can also rank the task importance. And before you submit, you need to first log in, like this. After logging, you can see all your previous submissions in your profile page, and you can choose one submission to show on the leaderboard. To submit new results, first you need to fill your model information like this, and then you select the prediction zip file here containing all the prediction files for each task whose format is described in the S3PL repository. Okay, and after you upload the zip file, this will take a while. Oh, sorry. Yeah. After you upload, the backend server will calculate the metrics and show the results on your profile page. And this one is our latest submission, and you can show it on the leaderboard. Okay. The end, and thanks for listening.
Okay. So due to time limitation, I'm only going to talk about one thing about our next step. In the near future, we will find a top conference to have a challenge. We will host a challenge about Superb based on the private dataset for the different tasks. For more information, please stay tuned on the webpage of Superb. we have not announced any information about our official challenge, but we will announce it in the future, so stay tuned. So this is all about Superb I want to share with you today. So now I'm going to give stage to Titouan. And Titouan, now the stage is yours.
Great, thank you. Thank you very much. So let me first share my screen here and here. Okay, right. So it should work now, hopefully. Yeah, thank you for the introduction and also for this first overview of this very, very crucial topic of evaluating our SSL models for speech in general, right? So here we'll continue on this topic, which is just assessing how well any SSL models, right, that you learn for speech is good for your potential downstream task with Le Benchmark. So Le Benchmark is an initiative led by 5 different institutions, around 20 researchers. So we also have a paper published in speech this year, and that's great. That's a lot of initiative around this crucial topic again, which is great. And so we all share something in common. It's our interest for the French language. So almost all of us are interested in doing research around the French language. And the thing is, if you keep this in mind, right, and you get back to SSL, from what we saw earlier, okay, we saw that unfortunately with SSL right now, we lack of scientific standardization. And this is capital because in the end, you might have maybe 5 new SSL models, right, with different architectures, or even let's say you have 5 different Wave-to-Wake 2.0 models that only differ in the number of parameters or even just self-attention layers or whatever, okay, just few differences. If all of them are trained in the same amount of hours, 3K hours of training in English, for instance, and the thing is, if this data slightly changes, right? Like one is based on Libre speech, the other will be based on Common Voice, another one on another data set, but they are all trained in English. It's become then super hard to assess which model is better and if it's due to the data or to the models, right? And if you combine this with the fact that maybe 95% of the models currently are evaluated on English only, you end up with a big problem in our case. I think it's in many cases in the end. It's almost impossible to know how well a new method that you came up with will work in a multilingual setup. When I say almost impossible to know, it means we don't know how to compare it to others. And this is problematic, right? Because when you see this paper, maybe the method is super appealing, maybe the data looks amazing, but yet you can't compare with things that exist in a standardized way. And so you cannot assess properly if this is a great step forward or maybe just nothing new. This is why we decided to go with Le Benchmark, and I guess it's also the same story for Superb and maybe others coming benchmarks. So with Le Benchmark, what we decided to do is to standardize both the data set and the evaluation, and we added French, right? So the fact of adding French is what will help you to go through multilingual setups, because once you have models trained in English and French, you can start assessing the fact that, I don't know, for a downstream task that is in French, English model are worse than French ones, or maybe just by, sorry for that, that are combined with French and English, right? Maybe multilingual models are just not as good as a French-focused one. And this is what we want to assess with the benchmark. So the very first step here is to build a standardized dataset. Remember that we want to evaluate new SSL models for speech, right? So when we come up with a new, I don't know, it could be a new submission to a conference or whatever. When we have a new SSL model for speech, we don't want to spend too much time or even waste a lot of time investigating the impact of the different data that could have been used. This is something we would like to avoid. And so to do this, well, with the benchmark, we offer a large enough and heterogeneous enough data set. So it means we provide the data, right? We standardize the data, so everyone will start with the same. So it has to be large enough because SSL needs a lot of data. If you compare it to, just like it has been said in the previous talk, right? SSL needs a lot of data compared to supervised training. For instance, you have to train a speech recognizer system. I guess if you have already 500 hours of labeled data, it can be considered as a huge amount of data to train your system, at least in the academic world. For SSL, we have models trained on up to 100K hours. So that's a lot of data. And then you also need it to be heterogeneous enough, right? Because if you don't do this, then you will close the door to a lot of different scientific questions that need to be asked and investigated. So you need to have something that will play with the gender balance, right? You will need to have a data set that plays with the influence of the environment, like noisy background or super clean background. And also the type of speech, because on the wild, you might see spontaneous speech or telephone conversations, or I don't know, not something that is only read by a reader that is in a sofa in a super clean environment with a good microphone, right? So you need to have all this in your data set to assess the impact of the data in future research. So the big problem here, and I think it's not only specific to audio, but it's really strong in audio, it's scaling the data. And if it's not in English, it's even harder, right? Even for French, which is not like a low resource language, it's super hard to get data for it. And so to approach this problem, what we decided is to gather all the different well-known French data sets that were around and standardize the documentation about them. So you can find in a single place all the information about different standardized set of data set with, I don't know, gender information, type of speech, number of hours, how it has been recorded, all this information. So when you do experiment with them later on, you can compare because you know all the information that needs to be known. And this is important for resources like in French, but I guess it could be the same for Spanish, and Portuguese, for instance, where you might have a lot of different small data set, like few hours, 10 hours. And if you combine all of them, then you can start creating huge data set. And this is what we did for the benchmark. So we have 4 different data sets, 1K, 3K hours, 7K hours, and 10K hours that is not released yet, but at least the 1, 3, and 7K are. And they are briefly presented like this. So the very first one, as I said, we have different amount of data, so 1K, 3K, 7K. And this allows us to work with questions that are directly linked to low resources languages, right? Like, are 1K hours enough to train your SSL system? Do you really need more than that? Like if you had, I don't know, 10K hours, will it scale well with the amount of compute you will have to throw to train this model, right? Or will the gain be something negligible? In which case you prefer to stay with 1K hours, right? Does it also depend on the downstream task? Maybe some downstream tasks don't really care about having 100K hours of training. Maybe just few K hours will be sufficient. And this is this kind of question that we'd like to investigate with these different sets we propose. The second point, as I said earlier, is the influence of the data type. And this is super important to assess scientific questions about production systems that will be deployed on the wild, right? So you would like to approach questions about all these SSL models we know out there. Do they perform well with spontaneous speech when they are deployed for, I don't know, speech recognition or speaker diarization, whatever. Maybe questions about the type of noise of the data as well. And like, is it really worth it to release a model that has been trained on 100K hours of only read speech, right? Will this affect the performance in the end on the downstream task? So this is why we decided to combine all these different data sets together. And the final remark I have here, which is not really specific to the benchmark, it's more general, but we're still having this problem of obtaining data because a lot of the data are still under licensing scheme, right? So few of the data sets we are seeing here must be required through formal processes and stuff to get the data. It's not fully open, which is problematic, but we can't do anything else. And that's for French. It could be even worse for, as I said, languages with fewer resources. And this is slowing down the research process and even, I guess, the industry. So hopefully this is something that will disappear in the next few years, hopefully, or decades, I don't know. But this is something to bear in mind, right? It's very hard to get the data. And this is why this kind of initiatives are important to the community to gather everything. The second step then becomes to, once you have your data train the SSL models, right? And here with the benchmark, we want to give the community a set of baselines to compare with. Why do we would like to have this trained model? Well, there are many reasons. The first one is research about SSL is not only about finding the best SSL models. By that, I mean the best SSL architectures, number of layers or type of, I don't know, attention you could play with, all this question. Some people are also interested in just applying these big models and see how they behave, just like I said earlier, to see if a model that has been trained on 3K or 7K will behave differently for emotion recognition or for speaker diarization. And this is why it's super important, because if they had to train themselves the model, it will become problematic, because training these models is not something that everyone can do. For instance, our large 7K model got trained on 64 V100 for 2 weeks. And this is the kind of resources that not everyone can afford. And it was even hard for us to get it. And if you think of like the 100K wave-to-wave-2 model that has been released by Facebook, I think it was mentioned that it was trained on more than 100 GPUs. This is a lot of resources, right? So some people cannot afford to play and train with this kind of models. This is why it's so important to release them. For the architecture, we decided to go with it's wave-to-wave. So there are many different reasons on the why we did it. The main, I would say the main one is that it's the only one that has been scaled that much and that have been already investigated that much by the community. But the point I would like to make here is that training these models is really challenging. Like sometimes the loss will explode, sometimes they won't converge. Adapting it to your own data sets might be hard, even because you are just playing with a lot of data, right? Like 7K hours of data from different data sets. It's a lot of stuff to manage, right? And so this is another reason why releasing models is important. You have to first gather the data, have the resources, and then play with the hyperparameters to make the model converge properly or obtain good performance. And all this is super costly for academics or anyone basically that would like to train these models. And you have more references on the actual architecture on the paper that is mentioned if you are interested, because I won't jump into the details here. So in the end, we released 7 different wave-to-wave-2 French models, right? So they are trained on French. So 7K, 3K, 1K, corresponding to the different amount of data we have, and large and base models that are just small and big models, basically. And all of them, of course, just like we saw earlier, can be used in all the well-known and your favorite toolkits, right? SpeechRun, ESPNet, S3PL, Thursec, whatever. You can just plug it, play with it, even evaluate them directly with Superb or with the benchmark task, whatever. You can do what you want as long as you just use the Hugging Face interface we provide or download directly the model. One quick remark here is this 2.6K that I did not mention. And this is exactly to answer the kind of question I was mentioning earlier, right? The 2.6K model does not contain any spontaneous speech. So it will help you to assess in between 3K and 2.6K what is the real impact of spontaneous speech, right? This is the kind of questions that we have to tackle now. Once you have the data and the model, then you can start doing the benchmark, at least for French, right? Because for French, we had to build everything because nothing was really already existing. Big problem here, as mentioned earlier, designing a benchmark close to the real world is extremely hard. In fact, if you just consider trying to answer the question of, I want to get the best possible, like universal representation of speech, it means that it should work with everything. And as I said earlier, it's almost impossible to tackle all the potential use cases that you will find out there. So to try to approach this, what we decided to do, and from what I saw earlier, it was the same for Superb, right? It's to put diversity in the middle of everything. First, we have the diversity of problems. We would like to try to tackle classification problem with emotion recognition, or conditional natural language generation, speech recognition, speech translation, or even sequence labeling with spoken language understanding. Then comes the diversity of information that is extracted. This is a very important point. So you have transcript for speech recognition, translation for speech translation, and paralinguistic for emotion recognition. This is directly linked to the quality of your representation, right? Because a downstream model that will do emotion recognition and another one which will do speech recognition won't look for the same information in your learned representation of the speech. One might be looking for emotion recognition, for instance, to loudness or prosody, while for transcript, they will be looking for maybe grapheme or grammatical related stuffs, right? So it is super important to be broad here. Then we have the diversity of annotated resources available. This is also super important because SSL models are most likely to be deployed on very varying levels of labeled data on the downstream task, right? You might have very small, like few hours, maybe 1 hour or less of labeled data in some use cases that you will find on the wild, while you might also find super large models, like for ASR. If you are doing now speech recognition in English, you have like tons of data that are labeled, so you can work with it, which is not the case, for instance, for emotion recognition, and even worse if it's in French, which is our case. So in the end, we just provide basically just like Superb, right? But in French, we provide a set of standardized downstream baselines with training scripts for emotion recognition, SLU, speech translation, and speech recognition. And you can find everything in our GitHub. You will have a new one certainly very soon for the NeRIP submission with more tasks. Yeah, I guess we won't see too much tables and numbers because there are many of them, and that's not super interesting. Let's try to directly jump into the outcomes of the very first preliminary studies that we did. Not, however, that all these tables and numbers are good for the community, right? This is the kind of stuff that we would like to see from a benchmark because it gives to the community, to the researcher, to the industry, to anyone that makes new models, things to compare with, right? Numbers to compare with, to know where we are with respect to the new model you come with or the new data you come with. So let's say that everything that is written in green is a behavior that we expected, while things that were written, that will be written in red are things that we did not expect to see in the experiments. So for emotion recognition, the first thing is that multilingual Wave2Vec 2.0 models that were trained on way more data than our French models did not perform as good as the French model. So language seems to have an impact here. Then for some reason, our smaller Wave2Vec 2.0 models, so the base one, led to better performance than the biggest one for the same amount of training hours, right? It's just the number of parameters. And as seen with Superb, right, SSL features in general are better than traditional acoustic ones. Here it was FBank. For SLU, you have so the same things, which is in gray, right? When it's in gray, it means that it was the same for the previous task. But we have two more information here. The first one is that more hours of pre-training do not improve the performance on this task. So moving from the 3K to 7K models, it was the large one, I think, did not improve the performance. So it means that we could have stayed with the 3K in this case, which costed us way less computation to train on, of course. And the second point is that larger Wave2Vec 2.0 lead to better performance, which is the inverse of what we saw earlier for emotion recognition, right? If we move to speech translation, so we still have things that are identical, but we have a new one, which is the fact that gains are now reducing with the increase of supervised data. So for speech translation, when we had to translate with few hours of label data on the downstream task, so here 25 hours, we saw a very large difference in between SSL features and FBanks. Like SSL features were way better. But as soon as we increase to this 200 hours of label data, then the difference between FBank and SSL features started to decrease, and it was all the way up to this amount of data. And when switching to ASR, it's the exact same story, right? So with all this being said, I can jump to the conclusion because I think we are quite on a tight schedule. Yeah. So here are a list of different outcomes that are exposed by this preliminary study. We cannot right now, nowadays, we cannot deploy SSL models from intuitions only, because it is clear that we don't really know well when a particular SSL models will perform better than another one. And even we could say when it will work properly or not. right? And as we saw, SSL models behaviors vary a lot in between tasks and in between data, in between everything. We have to be more precise and systematic about the study that we put on these models before deploying them like at a very large scale out there. And to answer all this, things like Superb and Le Benchmark and other initiatives that are unfortunately not that much currently are super important because they are needed to frame the development of these technologies and to answer practical questions about how should we use them in the real world, or how should we compare them when we deal with new methods to approach this problematic. Right. I think I'm done, so I will just hand over my colleagues for the open source toolkits part, right? So thank you, and let's discuss during the discussion period.
All right. Thank you, Titouan. Let me share my screen. All right. I guess you guys can see my screen now, right? Okay. So let's now talk about kind of general speech processing toolkit. So I will describe SpeechBrain, and then later Shinji Watanabe will illustrate ESPNet. But before diving into the specific toolkit, let me just summarize what is the role played. Sorry, that was the here. What is the role, right, played by speech processing toolkits in the community? Actually, this was very important role. Even before the advent of deep learning, the speech community, there were many very valuable toolkits, especially for speech recognition. I can mention here HTK from Cambridge, CMU, Sphinx, Julius, Raz from RWTH, Aachen, and Caldi, which is still used a lot these days. But at some point, with the explosion of deep learning, something happened, and we have seen also the community was building a kind of general purpose deep learning libraries, mainly based on Python. The first one was Theano, followed by TensorFlow and PyTorch. And thanks to this Python-based library, it was possible to create a kind of more general, more flexible toolkit. Some are rather task-specific, like, for instance, I can mention Asteroid for speech separation, PyNote for diarization, Sidekit for speaker recognition, and then many for speech recognition as well, like Deep Speech, Return RNN, PyTorch, Caldi, Espresso, and Lingua. Some of them, instead, are actually designed to address multiple tasks. And within this category, we can find FairSec from Facebook, which is actually a sequence-to-sequence toolkit. Then there is ESPNet and Nemo from NVIDIA, and the last member of the family, which is our SpeechBrain. So today, I will say something more about SpeechBrain, and then Shinji will tell you something more about ESPNet, and we will highlight, hopefully, the similarities and differences that these two excellent contributions have. All right, let me start with SpeechBrain. So what is that? SpeechBrain is an open source all-in-one speech toolkit based on PyTorch. The goal of SpeechBrain is to speed up research and development of speech and audio processing technology. We designed for that goal in mind. And with that goal in mind, we would like to have something which is flexible, easy to use, modular, efficient, and of course, with a good documentation. If you want, you can find here the resources that we have available, the website, the code, the tutorials, and the pre-trained models. I hope you can have it in the chat. Otherwise, you can just Google speech brain and you will find everything. But you can take a look at these resources during the talk. So what is the motivation behind this toolkit? So one peculiarity of speech brain is that we designed it from scratch to support multiple tasks. So we didn't start from one task and then we extended it to something else. What we did is to, from the beginning, right, we designed it to be able to digest multiple tasks. As we mentioned earlier, this is easier today than in the past because all the speech technology share the same underlying technology, which is deep learning. For instance, in the past, speech recognition was mainly using hidden Markov models coupled with Gaussian mixer models. Speech separation and speech enhancement were mainly using signal processing techniques, but these days they are all using deep learning. So these tasks are strongly interconnected, and we can create a single toolkit that manage all of them. And we call it speech brain to highlight this idea because we would like ideally to have a kind of toolkit that, just like our brain, is able to recognize speech, understand its content, but also figure out a kind of meta information about speech, such as speaker identity, emotion, language identification, etc. So what you can do with speech brain? So we already introduced some of these tasks in the previous part of the presentation. What we can do with speech brain is speech recognition. We have several models here: CTC, CTC plus attention, standard sequence-to-sequence models with RNN, RNN transducer, transformers, etc. We also have speech enhancement, which is about cleaning up an input recording. And here we have pretty good system based on metric GAN plus mimic loss. We also have the speech separation part, where here we have an input a mixture of two signals, right? Two speakers speaking at the same time, and we would like to separate them. And we have some models based on CompTasNel, dual pass RNN, and subformers. We also address spoken language understanding, which is about mapping an input sequence into an output semantic. And we also have a bunch of recipes for that application as well. We have speaker recognition, which is about identifying which speaker is speaking or verifying its identity. And we have some standard models based on X vectors, but also more advanced models based on the recent ICAPA TDNN model. We also have speaker diarization, which tries to solve the problem of who spoke when in a recording, such as a meeting, for instance. And here we have a solution based, our best models based on spectral clustering. But we can do much more. We can, in the current version of SpeechBrain, you can find recipes for language modeling, language identification, sound classification, graphing to phoneme, multi-microphone signal processing, and also EEG decoding of brain signals. So that's something recently we added because the toolkit is general enough. You can even use it for brain signal, for instance. And there is also a lot of work going on. We are adding text-to-speech, music generation, speech translation, voice activity detection, and also we plan to add finite state transducer using it's under development and integration with the Kali2 project, which is going to develop this finite state transducer, which are still helpful in the community when we would like to restrict a little bit the search. What are the design principles that guided us for that? Principle number one is we wanted something easy to use, right? To make it easy to use, we wanted to have some kind of modularity in the toolkit, where we try to design some kind of modules with intuitive functionalities, and these modules are designed such that they can easily interconnect with the other. When designing these modules, we try to be as Pythonic as possible and maximize the use of PyTorch routing, which is very important because PyTorch have this automatic differentiation plus GPU and CPU support. Another important characteristic is that we have tried to have a kind of lean software stack. We didn't want to add too many levels of abstractions. In fact, SpeechBrain is just built on the top of PyTorch without something in the middle. And also we designed such that any kind of PyTorch compatible code can be easily plugged into the recipe. For instance, into the mod into SpeechBrain, because for instance, if you are a general machine learning scientist, you would like to, you have your model, you develop your fancy model, and you would like to try on a speech task as well, you can just plug it in SpeechBrain and already see the results with that very easily. So another important part is that we tried to minimize the list of external dependencies. This is pretty good because we may want to have most of the things under our control, but this also can make the code easy to install, which is pretty good. Another design principle here is we want to we have special care on replicability and transparency. This is of course shared also with other toolkits like ESP.NET that are going in the same direction. So we would like to promote open and transparent science. And what we have done, we have released many recipes trained on publicly available data, such that the community can replicate. We are sharing our pre-trained models coupled with easy inference function using Hugging Face. But if user wants, we also have kind of gigantic Google Drive repository where we put all the logs and all the other information that are needed to reproduce the results. So that's a very important thing. So we need toolkits that we would like to go towards a kind of transparent and replicable science. Another very important characteristics that we consider a lot during the design is accessibility. So we released SpeechBrain with a very permissive license, Apache 2, which is the same as ESP.NET or Kaldi and even Nemo, I think, but it's very permissive. And yeah, we don't want SpeechBrain to be used only by researchers or very aware experts, but we want to be used by a large user base that includes students and practitioners. And we would like to use SpeechBrain for educational purposes as well. So just to give you an idea, I have used the toolkit last semester with my 60 students, and I asked them to develop kind of models for kind of challenging problems. And most of them, actually 58 over 60, they were able to finalize and successfully pass the exam. So I think we were, and these students didn't have specific expertise on speech. They had fair amount of knowledge of machine learning and computer science, but nothing specifically to speech. So I think we really achieved this goal, and I will encourage you to give it a try. So, but to make the code accessible, we need kind of comprehensive documentation, and I will tell you later about the documentation. Okay, so how can we train a model with SpeechBrain? It's very simple. We have many recipes and tasks, but in all the cases, you can train a model just writing Python, train.py, hparams.yaml. The hparams.yaml is the hyperparameter file. In SpeechBrain, we are using a kind of extension of YAML called hyperpy.yaml that we designed for that. And as you can see here, the YAML file, the hyperparameter file, is not a plain list of hyperparameters. Plain list of hyperparameters are not really transparent because you don't know who is using this parameter. Instead, in SpeechBrain, we, at the same time of the parameter declaration, we also declare the object that it is using this hyperparameter. So in the hyperparameter file, there is always a visible connection between the hyperparameter and the object using it. So once we read the hyperparameter file, we already have the object initialized and ready to be used. So this can make also the code more compact and avoid boilerplate code for initialization. So the hyperparameters files somehow decides which are the object, declares the object that we are going to use. Train.py instead decides how to combine these objects to implement the desired functionality. So here, the train.py rely on a special class called brain class, which implements the different stages of a training scripts. And one important thing here is that we tried to design train.py such that the most important computations that user will modify the most are visible. So we don't have to search somewhere else in the repository. In the main transcript, you already have the computation for the forward steps that converts the input into the output, the objective computation that converts the output into the loss, and also the data IO transformation. So these are directly visible to that. So maybe it's easier if I can very quickly show you some example. So let me share the screen. Okay, so if I go here, okay, all right. So let me see, for instance, Timid. One simple recipe is Timid ASR. So this is how it looks like the hyperparameter file for a simple experiment CDC speech recognition on Timid. So as we have seen before, right? The thing here is that we don't have like all the parameters have their link, like I don't know, NMLs, right? We declare NMLs, and we also declare the object that is using these NML parameters, which is the compute feature, and that's all. So here we can see we declare objects with their corresponding hyperparameters, and then we use this object in the main transcript, which is this one. The main transcript, as you can see, we have this special class. We make visible all the computations in the forward pass. Like here, we have compute features, normalization of the features, we compute some output, we perform some kind of model linear transformation, and finally we have a softmax. We have all the computation from input to output. Then we have compute objective, which is about takes input the prediction and gives you the loss. And all these computations are visible here. You don't have to jump somewhere else. And also we have all the data preparation part visible. Here, for instance, you have function that decides, that takes in input the wave path and read it. And you also have visible other functions, like the functions that encodes the targets into the corresponding numbers. Integers. So yeah, here you have also, you call the fit method for training, the evaluate method for tests, and that's it. So you can see it's relatively compact, and you have all the most important information exposed there. All right, very quickly, let me see. Yeah, that's part discover. We don't not only provide facilities for training, but once you have trained your model, you can easily perform inference on that. And for that, we created some kind of simple interface, and normally in just 3 lines of code, right? You can perform the needed inference on your model. For instance, here for speech recognition, you just have to call this interface. You call the hyperparameter with the model, and then you can transcribe your file. And in output here, you have the transcription. Same for speaker verification. You load the interface, you declare the class, and upload the model, and then you can verify if the 2 files are from the same speaker or not. And the same for speech separation. You have you load the interface, you load the model, and then you can perform inference on the mixture, and you will have the separated sources in output. So the most important models are on Hugging Face now, so you don't have to train the model yourself. If you want, you can exploit these version models, and we have currently 25 models on Hugging Face. Yeah, I mentioned before we did special care on documentation. So there are different levels of documentation. The highest level is tutorials. Tutorials are based on Google Colab and are designed to help newcomers not only to be familiar with speech training, but also to get more familiarity with speech technologies in general. And we are using Colab because people can run experiments if they want, or at least code snippets without even owning a GPU. We have many interesting tutorials. For instance, we have tutorial called speech recognition from scratch. Tells you all the needed steps to create a model, speech recognition model, speech classification from scratch, and speech enhancement from scratch. So we are covering different types of problems. But there are many more tutorials that you can take a look in the website. Another thing is the template. Templates are simple, well-documented recipes that contain all the parts necessary for a working system. And we have templates for different problems, sequence regression, sequence to sequence, and sequence classification. And that we think is a very good starting point for users to create their own recipe. They can just start from an existing template and modify them according to their needs. Of course, we also have doc strings. Here we try to for all the functions, right? We try to have a kind of uniform doc string that describes the function, the arguments, and very importantly, an example. So that's super important for the users to figure out the functionality of the function, to have an example showing it. So we have this for all the functions and classes, and this is pretty important. We try to stay aligned as much as possible with the documentation of PyTorch. Of course, you can also have inline comments, but that's not really surprising. For all these tasks, you can have kind of competitive or state-of-the-art performance here. For instance, we have good, we have reasonable performance on speech recognition, LibreSpeech. We are now 1.9 way to back. Timid, we actually have, this is the state-of-the-art. We have good performance on speaker verification, and also a very good performance on speech separation, which is actually the state-of-the-art that we achieved recently with the subformer. But yeah, you can have competitive systems here. Other features that we would like is that we support multi-GPU training, dynamic batching. We have nice support for large-scale experiments. For instance, we can now with web dataset, if you have a huge dataset which doesn't fit in your local SSD of your local computation node, you can leave it in the share file system, and we have these systems that can read efficiently from the share file system without slowing it down. We rely a lot on the fly data augmentation and feature computation on both CPU and GPU, and of course, we are now have support for self-supervised learning. And the approach we are taking is we have this interface with Hugging Face. We download the models from Hugging Face and we use it for fine-tuning. This project is started only 5 months ago. No, actually, we released the code 5 months ago. It started way before, and the project is kind of growing. We already have 46 recipes for 20 data sets. We have 28,000 star, 2,800 stars on GitHub, which we accumulate in just 5 months, which is pretty important sign of appreciation. And we are always looking for people that would like to help us with this project. So for further reference, you can take a look at our paper and our resources. You can find the paper on arXiv, and you will see many more things there. We have to thank our sponsors for giving us some kind of donation to hire students, the institutional partners, and of course, the core development team that works so hard on this project. So that's all on my side. So I will leave the stage to Shinji for ESPNet. Thank you very much for your attention.
Thank you, Mirco. And I would like to take over, and I would like to start my part of the presentation. Can you see my presentation? Okay, I think so. Okay, so let me start my part. My part is having a quite large overlap with speech brain, and I'd like to explain about a couple of the more like what would be the difference for the audience here to understand how our tools are complementary. And actually, these are more like a summarization of the various our kind of activities. So if you want to see more details about our the techniques, you can also refer some of the paper that are listed in this slide. Okay, so first, the ESPNet is actually the bit older than the speech brain. That we actually first committed it in the 2017 December. I still remember that time. And then that we first published a paper in 2018 in Interspeech, March. And at that time, that we had a couple of the toolkit, but we didn't have so much end-to-end ASR toolkit. So that is our kind of motivation. End-to-end ASR, end-to-end speech processing seem to be super exciting. And actually, I had a couple of the prior studies of this kind of a work, and I really would like to leverage such kind of exciting end-to-end experience to the community. So that's why we decided to make this kind of open source. And actually, there are a lot of parts similar in terms of the design and the so on with speech brain. But I just want to emphasize one different part. We actually try to follow and try to kind of connect the existing speech recognition researchers that are mainly working on the Cowdy that Mirco mentioned in his the first part of the toolkit. So Cowdy is actually at that time and still the very de facto standard speech recognition. So we intended to have a good connection with Cowdy, and that's actually also affecting our design. For example, the speech brain is based on the pure Pythonic approaches, and which is quite a modern approaches. Instead, what we did is actually having a bash script, the underlining of such kind of Python script, which is good in terms of the compatibility, scalability with Linux system and the connection to the Cowdy. But of course, we know that there are some limitations like Pythonic and hard for beginners and so on. And ESPNet is also getting gradually accelerated in these 3 years and having a couple of the visibilities in terms of the number of citations, number of developers now, the contributors actually over 100, and the star 4.1 thousand today. And yeah, compared with the other similar toolkit, we are actually in the same page. All are quite popular toolkit. Okay, we have internally some kind of the update from ESPNet 1 to ESPNet 2. But again, these are quite mostly the overlapped with speech brain. So I don't fully explain about the most of the things, except for the model 2 part. We actually still using Zenodo and having a very good kind of a function based on the Zenodo, but also have the limitation of the Zenodo. So I'm really impressed by speech brain that is free using the Hugging Face Hub, and I'm actually trying to kind of follow their style to working in the Hugging Face Hub, which is now ongoing. Okay, now that I move to the how the ESPNet covers the other areas. As I mentioned, ESPNet initially targeting to ASR Cowdy alternative as an end-to-end system. However, now it's actually cover speech translation, TTS, speech enhancement, and so on. That already explained by the other people as well, but I just want to emphasize why it is possible. This is because unified mathematical form of the sequence-to-sequence the problem, which is input is X sequence, Y to B sequence, or sometimes it can be just a category and so on. And then just have a transformation, right? This mathematical formulation is quite good for us to have a unified software design. And what we can do is, for example, changing the input from speech text that becomes speech recognition, text speech that becomes TTS, English speech to German text, it becomes speech translation, noisy speech to clean speech, it becomes speech enhancement. And then what we should do is, given this kind of unified software design interface, we just prepare the function, sequence to sequence function. That is actually quite the benefit of extending ESPNet from the ASR tools to the other tools. And also, I want to emphasize that especially the joint CTC attention, which is a little bit unique, the sequence-to-sequence model introduced for getting the ASR performance to be more stable in terms of the alignment. This actually becomes a quite big improvement without a lot of tuning. So this can be a little bit the different unique function compared with the other toolkit, although other toolkit also supporting this joint CTC attention. But the drawback of this approach is that makes the inference very complicated. Okay, so that's the kind of the benefit of the unified the formulation makes the unified software design. So again, many of the toolkit are now following this kind of design, the principle based on the mathematical formulation, and making this kind of exciting the model based the various speech solutions possible. And we are very closely collaborating each of the team actually. Now we move to the one of the main part, ASR. As Hui mentioned, ASR is a problem to directly converting the audio to the transcription. And this is actually history of our ASR benchmarking. And this is the error rate. So lower is actually better. And then as you can see that as time goes, the performance is performance improved. And there are actually two jumps here, and I'd like to explain that two jump. One is a transformer. As you know, transformer first started in the neural machine translation, and then later applied to the speech. And we are not the first the team to apply the transformer to speech, but we are the first one of the first the group that fully utilize the transformer the benefit, and we obtain a big performance boost based on the transformer. For example, we actually performed the benchmarking with the 15 famous speech recognition tasks. Some of them are very famous, some of them are standard benchmark, some of them are noisy, some of them Mandarin, some of them are other Japanese, and so on. And then surprisingly, among 15 tasks, 13 tasks, very large margin the transformer obtained to improve the performance. We are really excited about it. And this actually affecting a lot of kind of a benchmark competition. For example, this is the April 2019 Lively Speech benchmark, which is now the most standard speech recognition benchmark. And a lot of kind of leading research institute are comparing their performances. And then April 2019, Google released Spec Augment. That was an amazing result from the previous result. And everyone saw that it is very difficult for the other people to actually compete with this kind of Google numbers. However, this Google Spec Augment is based on the recurrent neural network. And we actually using a transformer and reaching the best performance, comparable performance by the open source community-driven effort. And to the model this kind of depict this kind of the things, I usually using this cartoon. This one is the Google or other giant, and this one is ESPNet. If we have good tool, we can compete each other. However, after that, actually this the competition continues. Google released the technique called conformer. That also gets the amazingly better performance from our best number. We didn't give up. We also try to follow. We actually re-implement the Google's conformer in our open source toolkit, and then apply to it not only for the speech recognition, but speech translation, TTS, all our speech applications in ESPNet. And yeah, there still have some small gap, but as you can see that we are now getting comparable, catching the soda of this kind of competition. Is the story ended? No. Actually, big jump happens again, which is the new weapon comes from the speech, the self-supervised learning, Web2, and Hubert, which is very, very strong. And then this was the previous best number that was now the updated by such kind of the self-supervised learning-based approaches. Do we give up? No, we still use that. Actually, this one, we have a great collaboration with people in National Taiwan University, Yi, and we actually using the S3PL super benchmark as our front end in ESPNet, and using the same weapon to compete with them. And then finally, again, we reaching the state of the art, the performance. So that is a kind of a very one of the good example that the academia or the communities can reach such kind of performance with a lot of help. But I just want to really emphasize that this is not only from our teams. We actually have a great help, great advice, and so on from the Google, Facebook, and also SPAV team also provided a very cool interface to use the self-supervised modeling. So I would like to use this word, the collaboration, which is a good example of the collaboration and the competition. In this example, would be a good one. And just discussing whether we catching the soda. Again, I usually should not give up to catch up that kind of soda. So I usually try to kind of follow that. And then we developed transformer, conformer, and Hubert, and so on. However, I really want to emphasize these are not our own activities. That's done by various other supporters and so on. So I'm really excited about this kind of the collaboration. And of course, now the self-supervised model are very easily used in ESPNet. So I'm already having a very good collaboration with SuperV S3PL, and I'm very looking forward to working with the benchmark people for this task. And I will also introduce some other activities like RNN transducer, which is quite good for streaming production system. And we have a couple of the implementation, various beam search algorithm, and so on. And we also started to support the K2 final state transducer-based beam search similar to speech brain. The other one, this is a little bit kind of unique. We also supporting non-auto regression modeling. This is, we don't need any beam search. We just have a one shot or some iterations to perform the speech recognition or speech translation inference. Beam search usually 500 or 1,000 of the lines of the code. It's only 20 lines of the code. Achieving the 0.03 real-time factor easily, although the performance it still have some small difference from the auto-regression model. But I'm very excited about this direction. And now I move to the other applications, TTS, which is synthesized the audio from the text. And actually, ESPNet TTS has a very good reputation. This is supporting a state-of-the-art, all the kind of the TTS systems. And also the neural vocoder can also be easily combined with the ESPNet TTS, and having a lot of example, the state-of-the-art system and real-time demonstration. And again, this is also helped by a lot of researchers to build this kind of ESPNet TTS system. I have a couple of the examples that like similar to the speech brain. We usually have a couple of the lines to just making the TTS and so on, but I just skipping it for to save our time for the presentation. And the voice conversion, we also have a voice conversion system, and the system is used for the voice conversion challenge baseline system as well. And we also have a speech translation that's changing the English speech to the German text or whatever. And we also have a very strong team to build the speech translation, the function in ESPNet. And that is actually quite intensively using speech recognition techniques based on the ESPNet ASR module to speech translation, and having a state-of-the-art translation performance in various benchmarking and so on. And all in one recipe are also available. And the last, speech enhancement is actually also having a lot of development. And this is one of the biggest change in ESPNet, including all speech enhancement function, like a speech separation, the beamforming, speech deliberation, the denoising, and so on, and having a demonstration and so on. And more of them are actually having a great help from the Torch Audio people. But this has a kind of strong overlap with the speech brain, so I kind of skip most of the demonstration. But the one thing I would like to mention is that the ESPNet SE is not purely designed for the speech enhancement. It's also designed for the integration of the speech recognition or speech translation, because this is one of our the absolute research goal. Cocktail party is not still completely solved yet, but to solve it, speech enhancement and speech recognition must be combined in the joint manner. Okay, let me summarize my talk. The end-to-end speech processing has a lot of potential, and the ESPNet, we try to make it to keep the state-of-the-art and reproducible research. Again, it's quite similar to the speech brain or other toolkit. And we are working closely with the other benchmarks and the other toolkits and so on. And we actually need more interactions with machine learning community. So I really appreciate if you guys have some input or using our toolkit, whether speech brain or ESPNet or Leaderboard or FairSeek and so on. And let's work together for the community contribution. And finally, I just kind of listing a couple of the discussion items that I had actually with Mirco, with a lot of kind of discussion, and then we saw that it is good to share. So first, everyone may kind of understand what is the different and what is the same. ESPNet speech brain has a quite common component, but I just would like to mention that our techniques, the applications are quite complementary. So I and Mirco just said that just use both of them. That is one of our answer about it. And then we also have a very common part, which is academic driven. That has some pros and cons listed here. So if we have some time, I also would like to discuss during our the forum time. And the last part is that I only mentioned that speech is one of the most important machine learning applications. So I would like to have a lot of input from you guys, how we should develop our toolkit and the baseline for machine learning researchers. That is from me. Thank you so much.
Thank you. So thanks, Shinji, for the great talk, and thanks all the panelists to share their project. So probably we take a very short break because we're running out of time. We take a 3 minutes break and we go back after 3 minutes. So we are offline, right? Are we offline? Okay, so after 3 minutes, we will be online, and all of us will have to open the camera, and we will all be shown on the screen. And I found that there are actually not too much general question from the audience, and some of them are specific and already be answered. So one thing we can probably do is, how about I ask some general question? For example, what is the next step of speech technology, or everyone think ASR or TTS already solved? What is your opinion? Something like that. Do you want to answer this kind of question?
I can basically answer if that no one that wants to answer.
Yeah, I can also talk about it from industry perspective.
Yeah.
Yeah.
I
how about my, yes.
Actually, that
Hello, everyone. Welcome back. Then let's discuss some questions from the audience. So the first question we are going to discuss is from Wei Cong Gao. Okay, the question is, it seems like most of the fundamental speech problems like ASR, TTS, voice conversion are solved. So what do you think is the next step of speech-related research? And what is missing for speech research now? So probably we start from Shinji.
Sure. I actually have a lot of answers for that. Actually, the one of the most difficult part for us is that our usual conversation. Computer is very difficult to understand it. Just in the quiet room or some little bit noisy room, but single speaker to speak to the computer, it can be solved and having a very good status. But for example, one of the example that I am actually working is the very natural smart home conversation, the environment. We call it chime challenge, and which is very, very, how to say, the everyday environment of the speech. And then we have a microphone array to recognize at the most 4 speakers are casually speaking something in the kitchen, dining, living, and we recognize it. Our first ASR result is 80%. This is error rate. Error rate is 80%. After during the challenge, it's improved a little bit, and now it goes to 40%, but it is way far from solving the problem. So just passively try to understand human conversation is still super difficult. And however, what I want to say is that then, is that a purely ASR problem? No, actually not. To understand the conversation, we have to tackle speech enhancement, speaker diarization. Also, we need to understand the audio event and so on, in addition to the speech recognition. So we have to solve everything in one system. How to do it? Human brain can do it. And the speech brain or ESPNet could potentially do it. That is my answer. Of course, there are several other challenging scenarios, but I can just give you one example.
Thank you very much, Shinji. So probably the next one is Mirco. Are you going to be the second one?
Yeah, I agree with Shinji. Actually, I would like to remark even more that, in my opinion, what is missing today is a kind of single framework for multiple technology. Like we studied somehow combinations of, speech enhancement, speech recognition technology, joint training, and all these kind of things. But I think there is much more, in my opinion, to be done in this direction. What about, for instance, cooperation between TTS and speech recognition? So, like babies, right? They learn how to produce speech at the same time they understand. So I think, in my opinion, there is a lot of space for good research in terms when we think about how we can combine technology, how this technology, the good technology that we have, can communicate with each other to achieve challenging goals like the one mentioned by Shinji, like conversational speech, etc. So I think this is a kind of big challenge and a big opportunity for good research.
Okay, thanks, Mirco. And Titouan, are you going to be Titouan? Are you going to be the third one? Thank you.
Yeah, sure. Well, I totally agree with everything that has been said. Like the most simple thing to me when I saw even in Twitter or remark about sometimes like ASR or TTS, all this stuff are solved. They are solved in the benchmark that not even purely solved, but in some benchmark that we are using, they are. Right? So ESPNet, SpeechBrain released all these models. You can take the models we have that perform 1.8% of what they write on LibreSpeech. Now try to apply it on your own speech, just your own speech. You'll see that you will have plenty of errors. Like it doesn't work in the end. And if you want to scale this into a production environment, it will be terrible. Like it won't work at all. And you can even just consider the YouTube subtitles, for instance, right? Even for English, it doesn't work super well. So if you consider other languages, it's just it's just terrible. It's like a plain show. So of course, like I think if we want it to work, we have to tackle the whole pipeline, like truly end to end, going from the signal to the transcription. So enhancement, diarization, ASR, and integrating language modeling in the mix. And maybe we will have at some point also consider to use some continual learning or meta learning to allow to improve the models over time instead of training everything on a single data set, right? Like there is no actual reason why we couldn't benefit from training model in LibreSpeech and then continuing the training in Common Voice and then training on GigaSpeech that has been released and still improving the results over time, which is to me a very important problem, like the time efficiency of our models. Yeah, that's it.
Thank you. And how about Daniel? You represent the industry part. You represent the giant part. You're going to say something?
Yeah, so I totally agree with previous 3 panelists. And I want to share like for more like a industrial perspective, we definitely see like ASR or even speech related problem is not solved. Because when you want to bring these problems into production, there are actually more things to consider. Like for example, Shinji mentioned the environment or latency or efficiency. If we want to bring all those problems to your edge device, how you can do the inference more efficiently and cover different kind of use cases, or more like privacy, or how you can represent more different kind of language or people they are going to use your models. These are definitely not solved, and not just a product problem, but also it feedbacks to a research community to more think about how they can make their model more efficient and represent more different kind of people. So I definitely like what Mirco and Shinji say. There's lots of combination of a technology we need to build, and it's not just combining the research, but lots of production things we can also do there. And it's not like a competition, but more like a collaboration. So we definitely see this. We should join our force in research and industry to bring this AI to more people.
Yes. So thank you very much for all the answers. So we know that those questions, the speech technology tests, are not solved yet. You still have lots of things to do.
Yes.
Okay. So my next question is also from the audience. Pre-training models have been successful in natural language processing and dominated most of the research. However, the pre-trained models for speech are not so popular yet. What are the possible reasons for the difference? And what is still missing for the speech pre-trained model? And I would like to make this question more generalized, not only focus on the pre-trained model. I would say, as we have talked about, we can use sequence-to-sequence model to solve all the different language speech tasks. But are there anything special in the speech community that is different from other modality that is special for speech? So who's going to start first? So how about Daniel? Are you going to start first? Probably you can talk about the special part of self-supervised learning in speech.
Yeah, definitely. And I think the others will have like great ideas. So, but in my personal viewpoint, I think speech usually we model in a more like a fine-grained levels, like on the friend level, and also in our speech problems, they are actually very diverse. Like we are covering maybe different languages or accents, or we want to not model. Sometimes we want to model the speech speaker identity. Sometimes we want to model the emotion. Sometimes we want to model the semantics. So those are very diverse, and so it seems to me there is still some way we need to improve our like current pre-training technologies to make our model better encode different kind of knowledge and in a more efficient way to attack the problem.
Yes, thank you, Daniel. And Titouan, are you going to talk about what is the special part of self-supervised learning in speech?
Sure. I think like Daniel made a very important point here, this aspect of having like multitasking as a general objective that we have on the downstream task. But there are also other things that I think are not only related to speech, but it's quite important still. Like in our downstream task experiments, we sometimes, if we really want good performance, right, we unfreeze the SSL model. So we train the whole SSL plus downstream model together on the task. And the problem is doing this currently with the technologies that exist. So for instance, Wave2Vec, it's crazily resources computationally intensive. Like you will scale your actual resources from one simple GPU to maybe 3, 4 on the same data set with even more VRAM. So I think efficiency here is a big problem because they are still very big. And finally, I think also we only saw quite recently very large speech SSL models, right? It's quite recent, like we're trying on 10K plus hours, it's few years, so it has to take off first.
Yes. So, Mirco, are you going to talk about in speech technology? Are there any special thing in sequence-to-sequence model besides just apply typical end-to-end model? Are there any special thing in speech technology?
Yeah, definitely. Actually, yeah. First of all, to answer the original question, yeah, as we have seen in this presentation, we already have pre-trained models for speech, which Wave2Vec, Hubert, and these are just amazing, and they are revolutionizing, in my opinion, the field, right? So we already have it; they are coming, but there are some specificity regarding speech that might make somehow even harder for a self-supervised model to capture the complexity of speech. Speech has phonemes. Speech has speaker identities, language, the language type, the emotion. So when we talk about speech, we are not talking about kind of plain text. We are talking about a signal which has a very, very rich information, and capturing in a self-supervised way this rich information without being guided by any label can be very challenging. But at the same time, we have seen that there are models doing that, like Wave2Vec, Hubert, and many of them will come in the next year. So that's a revolution, and yeah, that is going to change drastically the field of speech processing.
Yes, and Shinji, I believe you have lots of experience on that. Are you going to talk about what's the special part in speech besides end-to-end
actually,
model?
mostly people are mentioning, and what I want to add is that speech is waveform. So waveform has a lot of kind of physical property, and one of the kind of great but annoying things for us is a superposition. Everything is added. Noise, reverberation, and so on can easily contaminate speech. Noise reverberation, their variation is almost infinite. So this means that we actually have to consider infinite variations of speech. So actually, I have a very good experience of the Web2Vec's Hubert, but I also have a very bad experience of just feeding the Web2Vec and the Hubert without fine tuning to noisy speech like chime and so on. Yeah, performance was dropped. Yeah, but it was okay. It was okay, but the performance was dropped. I was expecting that 60,000 hours of the training data may somehow capture universal representation, which can also capture the speech in this kind of a very contaminated the waveform signals, but unfortunately not. But as Mirco mentioned, this is the beginning. So people may, of course, first we can do is to, the augment the data. Again, this is the benefit of the speech. Waveform, we know the kind of physical systems instead compared with the text. So we know that the exact the waveform equation, how it affects if we have a room impulse response and noise and so on. So data augmentation may be one kind of interesting direction. But besides, yeah, without so much data augmentation, whether still we can have a really universal the speech representation from such kind of very noisy the media is I'm actually really interested in. Yeah.
Thank you, Shinji, for your insightful answer. And there is, I have a question from Guanting Lin. So, is it possible for doing speech understanding without ASR, not rely on text and fully on speech content and prosody? Why we need spoken language understanding without ASR? Because Guanting Lin think there are some languages that do not have written text. So I know in speech community, there are lots of work that directly do the understanding from speech. So do you have any experience on this kind of test that you can share with Guanting? So probably we start from Shinji this time.
Maybe Mirco can.
Okay, Mirco. Okay, yes. Mirco, please.
Oh, well, yeah, of course. In speech brain, we have that, right? And we are just, we have these several recipes for that on Slurm, dataset, Fluent AI dataset, and many other, and timers and such that we recently released. And that's exactly the point. So you can really frame spoken understanding problem just like a sequence of sequence problem, where in input you have the input features or the input signal, and in output you estimate the semantics, the ontology, right? And that's it, without any ASR in the middle. And that works surprisingly well. In speechlearning, we have different recipes where you we call multi-stage or the couple, where you have also an ASR in the loop. But the best things we do is end-to-end, right? Normally, it's very convenient to pre-train some part of the network with an ASR, right? Just pre-training part. And this leads the best performance, but you can really map, even without pre-training, the input to the output semantics if you have a lot of data. Normally, for spoken language understanding, we don't have a lot of data, so you need some kind of pre-training, but it works amazingly well. So we learn the mapping pretty well, surprisingly well, because we created this data set, timers and such, with that goal in mind, right? And we realized that in the end, it's super easy. we can definitely learn this mapping very well. Yeah, so it's possible, definitely.
Yes, thank you, Mirco. I believe lots of the panelists all have the experience training this kind of speech to semantic model. Are there anything the panelists want to add up? Who is want to be the next?
I actually want to ask who is the opinion about it, because you have a lot of kind of speech understanding the research. So from your perspective, I'd like to ask, what is the end-to-end speech understanding is very cool, but I would like to ask your kind of opinion about it.
Yeah, because when I was a PhD student, my PhD thesis is about spoken language understanding.
Yes, that's what I mean to say.
In the ancient time, when people start to think about spoken language understanding, people think this question is so simple. This test is so simple. Just do speech recognition first. Then based on the result of speech recognition, then you can just apply a text-based search engine and get the result. But this is not true. Actually, sometimes you can observe the phenomenon that you have worse error rate, but better search result. Means your transcription is worse, however, the search result is better. So actually, ASR performance and the search result, they have some correlation, but they are not always the same. So optimize the downstream test performance is actually important. So if you can say we have a speech recognition system and we cascade with an downstream model, for example, search system, then you train it end-to-end, you can optimize the performance. In some cases, you can get better performance. So this is my basic idea. But when I was a PhD student, there was no end-to-end model. There was no
at that time, yes.
Nothing about deep learning. At that time, train an end-to-end model is kind of is not that easy. I remember that at that time, I tried to modify the learning criterion of the GNN HN model. I tried to modify HDK and spend a lot of time. But today, when we look back to the same question, it's probably easier than before. And before, when we want to do speech to semantic, it's kind of tedious. We do not know how to jointly optimize all the module. You need to do some math and write a lot of code. But today, with an end-to-end model, this is much easier. Input is speech signal. Output is the target you want. Then you directly train the model. But on the other hand, I'm still curious. Do you think those kind of speech to semantic model is is robust enough? Sometimes I'm worried that they are not robust enough. Probably they are just overfit to some specific tasks.
You do big error. You do epic errors sometimes. So sometimes, a small error in speech recognition doesn't care too much, but a small error in the semantic cares a lot, right? So, well, actually, we have presented a paper some time ago on using, the main problem is that normally the data don't have this semantic annotation, right? So what we did here is to use TTS basically to artificially create many data with the semantic annotation, and that was very helpful. So one can still try to minimize the errors with the data augmentation.
I see. But when you use TTS model to generate the synthetic data, does reviewer happy about it? I think reviewer will usually criticize when you use synthesized data.
Yeah, we actually use a mix of them, actually, real data. There's more real data, and we augment them with TTS. But it works, right? I mean, if you don't have too many data, you just take an external system for TTS and you do the best at that.
Yeah, because your testing data is real. So this is kind of like
the test data is real.
Yeah,
but you can fine tune the model or train a model with TTS data as well, and that helps, right? I mean, it might not be the best, but it helps a bit. Yeah.
Yeah, and to add on that, I think the robustness, stability is pretty important, especially for industrial products. So we usually do a lot of data augmentation to train your model on like different scenarios, or to make your model more robust.
Yes.
How about
yes, please.
Sorry.
Please go ahead.
Yeah, sorry. How about how to say? Yeah, end-to-end is great, and the TTS-based data augmentation is also great. Maybe the very good regularization, but I'm actually curious about who is the phenomena. While the error rate was worse, but getting the better result, which means that it's tried to capture more than the linguistic information, right? Some kind of the intonation, tone, and I actually also it's the first, end-to-end is great. We should definitely do it. But at the same time, I'm also curious that the so-called disentanglement of speech. Speech is, as Mirco mentioned, speech is capturing not only for the linguistic information, emotion, intonation, profile information, and so on. And somehow these are kind of, the good effect in the speech understanding, right? So that's why instead of we communicate with written by the text, but people usually recently do because by email, but people prefer to the talk. Which is because we actually, convey the more kind of structured information than the text information, right? And I actually also want to know about the spoken language understanding research can also capture these kind of things and also kind of analyze this kind of disentanglement of the speech, the information rather than linguistic information. Again, this is one example, TTS-based generation. Again, for me, it's good in terms of the regularization, but probably this would not do might not do more than that. If this TTS system is super cool and emotionally kind of, also the preserving the kind of the profile information, it can be, but probably this is just for the regularization in my expectation. And I just would like to have actually again, the Mirco and Hong-Yi about such kind of the more than linguistic information help the spoken language understanding. I'm just would like to know. Yeah.
Okay. So Mirco, are you going to go first?
Yeah. I mean, I agree. I mean, there's much more than plain text. There are many information that may affect the understanding, but it's mainly a data problem, right? So I know in Avignon they have this big data set for spoken language understanding. So I think if you would like to go in this direction, the main problem is data, right? We need data for
definitely.
And then with data, with end-to-end approach plus a lot of data, we hopefully are able to learn much more than rely on text, but also rely on other meta information, the emotion or all the other intonation, all the other information that mentioned. But probably we can do it only with more data than today.
Yeah, I totally agree with Mirco. This is also the answer I want to say, because we can imagine that intuitively, those kind of prosody information can be useful for spoken language understanding. Probably when you give an utterance, you will highlight the keywords. So when you see something is highlighted, something has stress, probably is the most important part, something like that. And you can find some paper in the literature that people try to show that we add this kind of prosody information that improves the performance a little bit. However, I think most of the benchmark corpus, they do not contain this kind of information.
Yes,
For example,
exactly.
I don't think ETIs have this kind of information. And even worse, there's another example. Our lab tried to do spoken question answering. And at that time, we do not have any spoken question answering data. So we synthesized all the data ourselves. The whole data set, also including the testing set, are synthesized by DDS. And you can imagine the reviewer are not very happy about it, but the paper is still accepted anyway. Then in this corpus, there's nothing about prosody. If you take prosody information, probably it will not be helpful. So I think probably data is the biggest issue here. Yes. Okay.
Yeah, definitely.
Yes. So, wow, I think we are chatting and running out of the time. Because we have to stop at 11 o'clock, I know there are many questions we do not really answer, but it's happy to chat with you guys. If your question is not answered, this to the audience. If your question is not answered, I'm very sorry about it. You can find the panelists in the speech or machine learning conference. Then in the future, you can ask the question. Or they also provide the link about their toolkit. And so it may be very easy to find a panelist. So it's fine that your question is not answered. Hopefully we have the chance to answer your question in the future. So due to time limitation. Yes, please.
Can I add one more thing? Just to show like a good like collaboration. So actually we're hiring and we if you're interested in like all the tools mentioned like a FairSec or Torch Error or more other things like Torch ecosystem, you can let us know. And I believe like Shinji, Mirco, and Hongyi and Titouan, probably you also like looking for talents people. So just share.
And for good sponsors.
Thank you, Daniel. And probably I have to give an ending. So my ending is, so today we learn a lot about speech. We see self-supervised learning can be helpful in all kinds of speech tasks. And we found that if you want to do something related to speech, you want to work on speech technology, it's not as difficult as you expected. So if you are looking for some domain you are going to work on, probably you are an undergraduate, you are interested in machine learning, but as you know, besides theory, to work on machine learning, sometimes you need to pick an application domain. And if you haven't decided which domain you are going to working on, you can consider speech technology. So probably this is the ending of this panel. Okay, so it's very happy to chat with you guys. And this is the end of Machine Learning Summer School 2021. We have to stop at here.
Thank you.
Thank you very much.
Thank you.
Bye-bye.
Bye-bye. Bye-bye.